Anybody? Really? I got emails. I guess nobody. Go ahead.
Could you just explain to me one more time what the K1 and K2 values represent in the current equation?
K1 and K2 for what type of problem?
The current equation across the inductor.
All right, he's asking about the equation that has K1 and K2 in it for the current through an inductor. I think the best way to answer this is with a problem. Anybody have a problem that they'd like me to put up? Yes? 443. 443. Thank you.
We did that last time.
He's pointing out we did that last time. Can we do something a bit more?
45.
Tricia. All right, I'm going to draw it up. While I'm doing this, what's the line in the game? Anybody know? Plus 3? Us? All right, good.
Like at least at
445?
That's what I heard was the best way to learn something. Let's give it like no, yeah, it's not.
All right, class, can everybody see it all right? You understand it? Now, I want to go through this. By the way, this is an excellent problem. There are several problems I assigned that really showcase some of the things you have to be aware of. So I want to make sure we can go through this and there are no uncertainties about how you approach it. The very first thing you do is look at the circuit for t less than 0. Does everybody understand that? I'll get to the K business in a second. So at t less than 0, maybe I'll put it over here, what the circuit looks like is this. Somebody asked me about this in my office. This is for t less than 0 or equal to 0. You got 12 volts. Now, because that switch is on since time began, it's a short circuit. I'm not going to show that. Now the inductors here, class, this is the important part. What do we replace the inductor with if nothing is changing with time? For instance, you guys are it's the best response I think I ever got from you guys. IL, and this would be for t less than 0. This is important. Now, I'm going to go ahead and just put the source in here. And 2 ohms. Oh, I don't even need to put that in. I want to just say one thing. The only thing you care about is the current in the inductor. Everything else doesn't matter until you get that. Then we get all the other information from that. Do you all follow me on this, class? Everybody. All right. So for this one, this is a short circuit. Now, this type of problem confuses people. I know I want the current there. I'm going to literally just get rid of that and make it a short circuit. Can everybody follow me? Now, this is real important. You'll notice there is that short circuit across that resistor. How much voltage will be across that resistor? Anybody? How many see it's 0? If you have 0 volts and you divide it by 6 ohms, you get 0 current. Do you all follow me? Essentially, that resistor can be taken out. Do you all follow the reasoning? If you do, let me see your hands. I want to make sure. Do you not see it there, guys? Right here, the 3 of you? Or not? Do you? I'm asking because I'm trying to help you. I'm not trying to intimidate you. Do you guys see it or not? No voltage, no current. Are you with me? Everybody. You realize whenever I put a wire across any resistor, literally there is no voltage possible. There can be no current through it. Everybody clear on that? I want to make sure. This is something that causes confusion. So I am going to do this to help you better understand. No current, no problem. Get rid of it. Yes? No current, no problem. Get rid of it. What it means is this, and I want to be as clear as I can. You have a resistor. Now just listen. All right? Just watch this. Here's a voltage. There's a resistor. I don't care what the value is. You ready? Just watch. I'm going to make this statement. I want to know the current through this resistor if the voltage is 0. It must be a trick. It's not a trick. What is the current?
0.
Does everybody understand why? 0 divided by any finite resistance is still 0. That's the reason. A wire just prevents any kind of a force, an electrical pressure to try to shove current through there. It eliminates it, circumvents it. There's a saying, and it's probably true in all engineering, current, water, whatever, takes the path of least resistance. Do y'all hear that before? Something like that? What that means is it's not going to go. Basically, if that's a short circuit, nothing goes there, it all goes there. That's my point. Got it? I want to make sure. By the way, I'm not trying to be a smart aleck. I'm trying to help people. All right? I'm not trying to point people out to embarrass them. I'm really trying to help you, but sometimes I just don't know how. But I hope we're clear on that. Now that we're clear on that, let's take a look at this. This is the current I want, right? What is that current? Now, think about it logically. Can we figure out the current this way? What is that current and why? Anybody? Why? You're right. You said, and in so many words, go around the loop. There's 0 volts here. So plus 12 minus that current times 6 has got to be 0. That current, somebody said 2 amps, right? Put 2 amps there. All right. Not quite done yet. How much current is flowing this way?
3 amps.
Why? You're right. Remember, this is 0 volts right here. So increase of 6, you can assume the current going that way, minus 2 times that current equals 0. That current is 3 amps, right? How much current is going here? Can everybody see the reason for it? How many can? I'm really going overboard on this one, but this is the kind of problem. There's something that seems fishy. I just don't trust that problem. It's not. Just feel confident. Your reasoning is sound. It's 5 amps. All right, so we got, and I'll put it up here. You asked, I'm trying to answer your question. First thing is what? ILT less than or equal to 0, 5 amps. Everybody got that? Who asked about this problem? Whoever did deserves an award. This is a great problem. I needed to talk about this. You just gave me all the ammo I needed. Ready? Now, the next thing we go is flip the switch, whatever it's doing, and find out what the circuit looks like then. Now, do you mind if I erase that? So I have a little board to work with over. So I'm going to get rid of this thing. Now, I'm going to open the the switch, and I'm going to do something better than that. I'm going to erase the part of the circuit that's of no value. When this switch opens, is there any way this circuit can influence that circuit? Why? You're right. It's connected at one electrical point. It has to be at 2 to force current. Does everybody follow me on that? All right, so I'm going to do this to make your life and my life easier. Now this is what the circuit looks like at t greater than 0. Y'all follow me? All right? The next thing we need is what? We need the current IL as t goes to infinity. Please just go with me on this one. Work with me. What do we replace the inductor with here? Wire, short circuit, right? Anything of the sort. So if it looks like a short circuit, and by the way, you always have to be sensitive to the polarity of current. Remember, my current is going from the top to bottom. So that's the current I will always want. Don't reverse the direction. Are you with me, class? So what is that current going to be and why? You've got 6 volts, you've got 2 ohms, it's got to be 3 amps. It has to leave the positive terminal. It's got to go like this, right? That's 3 amps. How many see that? Be confident in your reasoning. It's not hard to see this, but people have this natural paranoia. Something must be amiss. It can't be that easy. Idiots. All right, so this is 3. All right. Now, that's still the circuit. I'll get rid of that wire in a second. That is for t greater than 0. Are we clear on that, everybody? Let's get rid of this. What's the next thing I need? Well, I need R Thevenin. You're ahead of the game. Tau, you need R Thevenin for. I'm trying to just do this methodically. Everybody with me? Now, by looking at that, this one's pretty obvious. What do we do with this source? Short it out. It's a voltage source. If it was a current source somewhere in there, then you would just simply remove it. Y'all with me, class? You turn them off. You turn a voltage source off. It's a short. You turn a current source off. It's an open. R Thevenin is 2 ohms. Now, what is the time constant for this circuit? L over R, always proportional to either the inductor or capacitor. When you have an inductor, it's inversely proportional. R, so the time constant here, tau, is equal to L over R Thevenin. And what was L? 2?
Yes.
Was it 2? So this is 1, isn't it?
Yes.
1 second. Correct, class? Now you asked about the time constants. Finally, you write the equation for the current in terms of the unknowns. IL as a function of t, and this is for t greater than or equal to 0, by the way, is equal to k1 plus k2 e to the minus t over tau. That's the equation. I want to make it clear, that's it. No tricks. What is k1 and the reason for it? Anyone? Yeah, but it is the current at t equal to infinity, right? Because the other one, the e to the minus infinity, makes the other one go to 0. So if I put, y'all with me on this? I'm just going to put it, you said 3? I'm going to take your word. Now, at that point, the only thing you have to do is evaluate that equation when the switch transitions. Are you with me? That means the current is the same before and after the 0 point. You with me, class? It can't change instantaneously. That current was, I think I put it there, 5, right? Now just look, if I put 5 on this side at t equals 0, equals 3 plus k2, right? K2 has to be 2. Are we clear? Everybody, just take a moment. I I want to make sure there's nobody that has a question about this, because this is the problem. There's a lot of times, people that are just, there's something that is not feeling right. And they don't know how to formulate a question to ask me. But think about this. Are we clear on this? If you've got a question, now, yes, sir.
If t to infinity was 0, then k2 would be 5, correct?
You hear what he said, everyone? He said, well, what if the current at t equal infinity is 0? Can't we just look at this equation? I mean, if this is 0, then the other one is the current at t equals 0, right? That's what he's getting at. Do y'all follow me, class? He's just asking a question that seems obvious, but he stated it in a way hopefully can help somebody. There are always these little nagging questions you have, and you don't know how to ask them something. Now that's the current. Please listen to this. Here's another mistake I'm going to show you that happens all the time. Now, you'll notice this current, once I put in the thing, when I put the inductor back, we have this current, right, IL of t, for all time greater than 0, right? You'll notice the direction it's circulating like this. Everybody follow me? That means, in a simple sense, forget about what they're asking over there with the polarity. It will generate a voltage plus to minus, and I'm going to call it V prime here, on purpose so you see it. V prime here would be 2 times IL of t. Now I can write that, I can go ahead and multiply it, you get 6, right? Plus 4 e to the minus t over tau. Do you all see the signage I put down there? Now they don't want that. They want this. So the negative is where the positive actually is, and the positive is where the negative is. What do we do to the actual value of V prime? People? Multiply it by a negative sign and voila. Correct? Did you have a question?
No.
Does everybody understand that? It really is that straightforward. And don't make these things, it must be tougher. It isn't. These are simple problems. They're very simple. The only thing you have to do is understand the concepts, and you'll have no problem. And have faith in yourself. Okay, you got another? I hope that answers your question. All right, now listen. You know, on the exam, I get these questions. When is the exam? I don't know. You're going to vote on it. I think I mentioned it, didn't I? How many know you guys are going to vote on the exam? I thought I mentioned it here. Yeah, you know what you're going to do? When we're getting close to the end of this chapter, I'm going to ask somebody in here, probably you, to count hands with me, and I'm going to say, when do you want it? And some people will come up with dates, and I put the dates up there. And we vote on 3 dates. And the top 2, we do a runoff in here, and she counts hands, so I don't mess it up. And then that settles it. So you're going to vote on it. What I suggest is this, because we got a bunch of different types of engineers here. Look at your calendars and keep thinking downfield, when would you like it? Hear me? And don't come up with some screwy date like after the semester's over. I mean, something that's reasonable. And I'm going to make one suggestion. I finished chapter 4 for a reason. At the end of chapter 4, then most of the, you might say, the conceptual things that are threatening are covered. Now it's applications to specific systems. Y'all hear me on this? After that point, I don't care when you have it, but now you've got what you need to cover. And by that time, people ask me, should it be after Thanksgiving or before? Before. After fall break or before. I don't care. At that point, it's up to you, because it's how many tests you get in 1 week. And I don't recommend you take like a test in here than a test in thermo or fluids or something. Try to at least schedule 1 test a day if you're given the opportunity. Y'all with me, class? So just a suggestion, but you guys are going to figure it out. Now, last thing I'm going to cover is I want to go through and I'm going to show you how simple the next chapter is, because you're going to probably look at me like that seemed really crazy with that J business. Now I'm going to show you something, and I want you to be attentive. Some of the steps I was outlining, but I'm going to get to the point. I'm not gonna, you know how in this stuff we wrote differential equations? Oh, we could write all these differential equations. So, do you need differential equations, class? We have the form of the solution for both inductors and resistors and capacitors and resistors. That's all we need. We can care less about diffie-qs. No Laplace transforms. I better not say that too loud. I wish you could edit that out of the recording. But anyway, the fact is, what we care about is knowledge of how to solve the class of problems that are coming at you. You don't have to solve every single kind of problem. You'll go nuts. Right now, it's the transient problems, and they are something of interest to, I think, most engineers, because that's what you're going to see in the real world a lot of times for timing circuits. All right, now, I'm going to show you stuff. You got the quiz, I know that. But I want to just cut to the chase on this one so we don't have any problems. And please watch this. What I'm doing here is giving you the Cliff Notes version that I wish I had when I was where you were. You are. All right, first, an inductor. You got an inductor L. I'm yet. I think I'm going to go to the bookstore and just find a bunch of these things that work. Buy the whole box, charge the department. If I get in trouble, I get in trouble. All right, there's a voltage plus to minus V across it as a function of T, and a current I of T. The relationship between voltage and current for an inductor in the time domain, this is going to be time domain, is simply L times the time derivative with respect to T of T is equal to the voltage V of T divided by it. Y'all with me? That's it. I'm just curious. How many remember that from physics or from something I put on the board? Most, well, a fair number. Now, if you take a look at this when we go to constant frequency, now we're not talking about something that may have a variable frequency or is a transient. We're talking about a constant frequency. So when you have some frequency f given rise to some value of omega that's 2 pi f, you all follow me on this? 60 hertz, that would be 120 pi radians per second would be the actual radio frequency of the wall outlet. Y'all with me, class? Now, if you have that, this relationship here becomes V, and the symbol is phasor over I phasor. You don't need to know that, but that's an impedance. The symbol for an impedance, this is a complex resistance, that's all you think of, is going to be Z, and I'll put some L here for now. And what that is, if you look at this, whenever there's a time derivative, you bring out a J omega. Both the current and the voltage will have the same time variation, e to the J omega t. I'm going to leave it like that for now. What this will break down to is J omega L. And the units of this are ohms. I was getting at that last time. I'm very curious about this. How many have seen something like this before? You got the spattering of hands. You probably have been introduced to some. That's called an impedance. The units are ohms, but that J is key. J tells me it's an imaginary quantity. Another way to write J, and this is in the frequency or phasor domain, J is actually a value of e to the J pi over 2 radians, or e to the J 90 degrees. Now, if you are unfamiliar with complex notation, don't worry about it. I'll show you what you need to know. How many have had, imagine the J business, the square root of -1? If you're an ME, I know you've had it. I'm familiar with your coursework. Most people have in your math courses at some point, but I don't know. It's usually an I. Remember that discussion? It's not usually labeled as a J. They're interchangeable, same thing. Now, when you look at this, that means this inductor looks like this. Now, a capacitor in the time domain, you have a voltage VC of t, and you're going to have a current I of t here. Here, it's C times dV dt, is equal to I. That would be in the time domain. In the frequency domain, where we're going, this simply becomes V over I, and this, they're shown as phasors. This is across the capacitor. Will be, and I'm labeling it as Z sub C. The sub C means related to the capacitor, and that is equal to 1 over J omega C, and 1 over J is just minus J. Now, I know some of you are a little uncomfortable with that. You will get over that. Y'all with me? How many have seen something like that? You've had to see this if you're in these. I know that. I don't know, I think it's probably the lab, but I'm not sure. So what does that ultimately mean to you? Well, let me show you. And I'm going to do this in a way where hopefully you'll understand and appreciate how you eliminate the need for writing differential equations. And now we solve very trivial algebraic equations. And then you will get your quiz. So let me show you this in a nutshell. I'm going to put a voltage here. I'm actually after the current I of t. I want the current in the time domain. This voltage has been on forever, and it has a value of V naught cosine of omega t volts. Y'all with me? The symbol for this usually is just a very small snippet of a sine wave so that you know it's time varied. That's the only thing. Now, without going into it, we could write the differential equation. We could say an increase of V naught cosine of omega t minus I of t times R minus L times di dt equals 0. And then we could use either Laplace transforms or tricks with integration factors, or we could solve it. And you could do that. But why do that when you can go right to the phasor domain, get the answer, and then go back to the time? Now watch this. So instead of doing that, what we do is we show a source. And the only thing we care about is the magnitude of the source, which is V naught. Now, I didn't say this, but if there was a phase angle in here, if there was a phase angle, then you would have to add a phase angle there. Do you all see that? How many understand that? This is complex notation or polar notation. The next thing you would do, and this would be plus to minus, a resistor will look like a resistor in either the phasor or time domain. There is no change. So you put the resistor. Y'all with me? And finally, instead of inductor having a voltage of L di dt, you simply show an impedance. And the impedance of that inductor is going to be J omega L. The units are ohms. Are you with me? This is in the phasor domain. I'm cutting to the chase. I'm not going to give you a whole bunch of abstract ideas. Now, this here, it's at an angle of 0 degrees, gives rise to something called a phasor current. I'm going to use capital letters here with a little tilde it really indicates you're in the phasor domain. That's all it means. When I want I, and I got a voltage, that value of I will have a magnitude and a phase. Just listen to me. So, to get I, as before, you start with the voltage forcing the current. You all with me? It's a single loop. Everybody got that? You put that over here. That voltage, which happens to be just V naught, and then you divide it by the complex resistances. That's R plus J omega L. Can everybody follow? Now, that will render a polar number, magnitude and angle. How many have heard of polar numbers or exponential notation? Every single person in here has been exposed to it if you had math here. I don't know if you remember the terminology. It would be like 20 at an angle of 30 degrees, something like that. You with me, class? It's called polar notation. For this one, it will have a magnitude and an angle. So it will have a magnitude of I, and there will be an angle associated with I. I'm going to show you how to get both. You all hear me on this, everyone? Get this down. I'm cutting right to the chase so you don't have to ponder some of those weird discussions. Now, to get the magnitude of I, and I'm going to put that over here, that's a complex number. Listen, you have to square this value, and then forget the j, square this value. They are 90 degrees apart from each other. And I really don't want to spend too much time. And then take the square root. So the magnitude would be the magnitude of this, which is just v naught, over, and it would be the square root of r squared plus omega L squared. Now, that will give you the magnitude of I. Can everybody hear me okay? As far back can you guys see it? All right, the angle, you have to get by first getting the angle down here. And I'll try to make sense of this one for you. So if I looked at something, and this is the real axis, and this is the imaginary axis. I have a resistance R here. This is this value. The vertical axis is the imaginary. If I come up this way, I have omega L. Frankly, it's j omega L. Do you all see the rationale here? Now this hypotenuse right here is the square root of r squared plus omega L squared. Sorry about my writing. Y'all with me? You can't see it? I'm just making sure, because I realize I'm shoehorning this in here. This is the angle we need, right? That angle would be on the bottom. That's an inverse tan. How many see that? Opposite over adjacent tangent. So the angle down here would actually be inverse tan, or tan minus 1 of omega L over R. Can you all see this right here? That's not a minus in front of it. With me? Angle on that is 0. Can you all see this, class? Far back, guys. I'm almost done. Now, to do justice, you put the magnitude out in front. And then, what happens when you take an angle from the denominator to the numerator? Anyone? Sign changes from a plus to a minus angle. How many remember that? Yeah, sure. This is just going to be an angle of, then there would be a minus tan minus 1 of omega L over R. Now from that, to get to the time domain, I'll show you next time, but it's trivial. What you're going to see is, when you do some of these problems, and do them by just replacing the components with their complex impedance, and then doing it like you would every other circuits problem, you'll get the answers, and it will become almost too obvious. All right, now, at that point, everything off your desk. Take your